In previous videos, we've looked at some of the claims that have been made about exoplanets and had a look at what affects the resolution of a telescope. Now, we're actually going to have a look at the way that we get information out of the images from our telescopes. The source of all this information is from breaking down the light from a star into its spectrum. The rainbow of colours that is produced will be brighter in some areas and darker in others. This pattern allows for the behaviours, compositions, and temperatures of objects to be determined. Here is a bit of a rundown of some of the things that can be found just by looking at the rainbows of distant stars. We've all seen objects that glow red hot, and most people would be aware of thermal cameras that can see the heat produced by your body. This effect of objects emitting light based on how hot they are is called black body radiation. When we break down the light from stars, we can see the pattern of black body radiation in the brightest parts of their spectrum and the highest frequencies of light that they're able to produce. This can be seen as the overall color of stars, and it links directly to their temperature. Red stars are dimmer and cooler, blue stars are brighter and hotter. Spectral lines can be used to identify the elements within a star. This is a lot like the flame test you might have done at school. In this test, chemicals are heated in a flame, and each chemical will give off a different color of light as it glows. This is the same process that gives fireworks their color. In astronomy, we can use this property to identify the elements that make up objects. Each element is able to absorb or emit a specific pattern of frequencies of light. By looking at the light coming from distant stars and looking for the signature pattern of each element, we can determine what the stars are made of. When a fire engine or ambulance drives past you, you can hear the change in pitch of the sound it makes. This is known as the Doppler effect. The same effect happens to light. If an object is moving towards us, we see the wavelength of light compress slightly, so it looks bluer. If the object is moving away from us, we will actually see it looking redder than it would normally be. But if the object we're looking at is a star, how can we tell whether we're looking at a star that's moving towards us or a star that just happens to be slightly bluer? The answer comes from the spectral lines that we looked at before. If a star is moving, then the entire pattern of spectral lines will be either red shifted or blue shifted, depending on the star's movement. In an ideal case, the spectral lines that each element form will be at an exact wavelength. However, there are many factors which actually cause these lines to stretch out and become wider than they would be expected of. There are a few reasons for this line broadening. The first is from quantum effects. Because these always occur, they produce a minimum width that a line will be. Lines can also be made broader by their temperature. When a gas heats up, the particles in that gas start moving faster. They will sometimes be moving away from us and sometimes be moving towards us. This causes each particle to have its own Doppler effect, making its light slightly bluer or redder. The result is that the lines we see become broader than we would expect, following a Gaussian distribution. By looking at the amount of thermal broadening of spectral lines, we can get another estimation for the temperature of our star. When added to our information from the black body radiation, we can start to get a really good idea on what the actual temperatures of stars are. Spectral lines can also be split by magnetic fields. This results in each line having an additional line before and after it. By looking at the intensities of these lines, we can also get an estimation of the strength of the magnetic field that is around the star. Finally, as the light is traveling towards us, it may pass through other gases, and this will also change the spectrum of light that we see. By looking at the increases and decreases over ranges of frequencies, we can make estimations for the size of molecules or even dust particles that the light is passing through. This is particularly useful when we're looking at planets, because we should be able to see the periodic changes as the planet orbits around the star. As more observations are made and new techniques are developed, our understanding of these stars and their planets is only going to improve.